Hello, my name is Benito Ramirez Vasquez, and today I'm presenting my network design proposal for the Vinculacion building. Over the next few minutes, I walk you through the elements involved, how the network was structured, and why I believe this is the right solution for you as the client. Before getting into the routers, let's talk about what this network actually serves. This building has two kinds of elements that need addressing: human users and IoT devices. On the user side, we have students, administrative staff, faculty, and guests. On the device side, we have lamps, fans, coffee makers, humidifiers, appliances, and servers. Every single one of these, both people and objects, needed a public IP address because the project required a public addressing for every node in the building. That single requirement is exactly why BLCM was the right tool here. Instead of giving every group the same fixed block of addresses, BLCM lets each group receive exactly the number of addresses it actually needs, whether that's 4,000 student devices or just five servers. And here, a small design decision that made a real difference. Organize BLCM from the largest group down the smallest student spheres and administrative staff and faculty and so on. All the way down the servers, the reason is simple. And when you allocate from biggest to smallest, every block fits perfectly right after the previous one with zero wasted addressing in between. If you try it to allocate in a random order, you end up with gaps that don't align with clean subnet boundaries, and whole addressing table becomes harder to read and harder to expand later. Organizing in this way also makes it much easier to identify the characteristics of every element is a glance. You can look at the table and immediately tell which group is which, just be size of its blocks. Now let's talk about the architecture. The backbone is a chain. The central router connects directly the floor one router, and from the floor one connects onward to floor two, and the floor two connects onward the three. That means floors and three depend on floor one to reach the central router and from where the rest of the network. Each the center this connection use a dedicated slash third subnet, the smallest possible block. Since a serial link between two routers only needs two usable address. From each floor router, design branches or truck is a gigabit interface into a chain of additional routers, each one highly two of the building's groups. Every floor repeats the exact same structure, same number of routers, same group assignment, same logic, which makes the design predictable and easy to document. For routing between all these devices is used ARP, a Cisco routing protocol. The automatically discovers neighborhood router and calculates the best path to every subnet with no me typing a static route for every destination. With more than 30 subnets across this one building, static routing will have a mean dozen manual entries per router. IGRP removes the risk entirely. Now here's a detail that shows the seriousness of the design. In packet tracer, I only placed two switches for the student group because the simulation does need every physical device to prove the network works, but that's not what will happen in the real life. A standard access switch has a 24 ports, and this building has 4,066 students per floor. Doing the math, And this Ford 1066 divided in the 24 comes to regular 170 switches, not to use the physically connect every student computer on single floor. I wanted to be transparent about that from the start because I cleaned the servers to know the real infrastructure scale, not just what fits neatly on a simulation screen. So what does a design to get right? First, the IP efficiently builds them organized from largest or smallest, means every group gets exactly the address it needs with clean, graph-free allocation that's easy to read and easy to expand. Second, scalability. Because SRP is dynamic, adding a new floor or a new group requires almost no reconfiguration of the existing network. um, Advantages. Um, I want to be equally honest, but the trade-offs. First, the chain structure creates a real dependency since the floors 2 and 3 really floor 1 to reach the central router is a floor 1's connection every goes down, but of the other floors lose access to the rest of the network at the same time. That's a single point of failure that clients should be aware of. And this design is generally costly and full scale. Once account for the number of switches needed per floor, plus the cabling, rack space, and power that come with it, real hardware. Investment is significantly larger than simplified diagram suggests, and needs to be budgeted for honestly until the IoT devices in the network don't configure themselves the way a PC does. Each lamp, the coffee maker, humidifier, printer, and the servers at each IP address and gateway set manually one device at the time, which a real setup effort compared to endpoints that can request their configuration automatically. So why should you choose the proposal? Because it solves the actual problem, and you have a larger mix of users and devices that all need a reliable, organized, and scalable connectivity addressing efficiently instead of what fully the BLCM structure leaves room to grow. And the routing protocol remove the burden of manual maintenance for your IT staff. And honestly, I bought real switches counts, real dependencies, and real device configuration. And for means, you can plan the budget correctly from day one instead of discovering hidden costs and hidden risks once the project is already on the way. This is just a design that works in a simulator. It's a design built with your actual scale, your actual devices, and your actual future in mind. Thank you for your time.